In this problem, we look at the behavior of a special purpose shift register. Important concepts for this problem include the behavior of D-type flip-flops and an exclusive OR gate. Now the problem statement tells us the initial state of the three flip-flops in the shift register. It says that the value in this flip-flop is 1, and in this flip-flop it is 0, and in this flip-flop it is 0. This is our initial state. We're then looking for the successive states. That is, what are the stored values in the flip-flops as we begin to apply clock pulses. Now we see that the clock input of each flip-flop is wired to a common input called clock in. The clock is a periodic pulse train, something like this, in which each rising edge of the clock causes the flip-flop to be triggered. Now what does that mean? Well, when the flip-flop is triggered, it stores whatever value is presented on D, and it maintains this value until the next clock edge. So we see that these presently stored values are available on the outputs. So we see that a 1 is applied to this D input, so on the next clock edge, the stored 0 will become 1. Now in this case we apply a 0, but it's already storing a 0, so there's no change. These values pass through the exclusive OR gate and produce the input to the first or leftmost D flip-flop. Let's take a moment here to review the behavior of the exclusive OR gate so we understand how it responds to its 4 different input possibilities. The exclusive OR gate produces a 1 whenever its inputs differ. So we see that this case and this case produce a 1, but when A and B are the same, then we get 0 coming out. So 0 is applied to the D input of the leftmost flip-flop, so that means that on the next clock edge, that a 0 will get transferred into the flip-flop. So we are also directed to find the number of clock cycles or number of shifts until the stored value returns to its starting point of 1, 0, 0. Let's begin by recording the initial state of the flip-flops. So we have 1, 0, and 0. Since 1 is a stored value, this value is made available on its Q output. Similarly for the other 2 flip-flops. And as we consider what happens as the signal flows through the rest of the circuit, we recall that the exclusive OR gate produces a 1 whenever the inputs differ. So in this particular case, it produces a 0. So a 0 is queued up at the input of the leftmost flip-flop. So let's keep track of the behavior of the 3 flip-flops in terms of their stored values. So if we've not applied any clock edges yet, or we could call this clock edge 0, that's the initial state. Now the lead flip-flop is seeing a particular value of 0, but let's see if we can generalize what value will always get applied. And we see that it's Q1 exclusive ORed with Q2. D1 always sees whatever is in Q0, and D2 sees what is in Q1. So that describes how to calculate the inputs to each of the 3 flip-flops for any particular value. Then on each clock edge, Q0 becomes whatever is applied to D0, Q1 becomes whatever is applied to D1, and so forth. So as we consider, say, a single rising edge of the clock input, that causes, in this particular case, a 0 to get transferred in and a 1, and it was 0, so it remains 0. So our new state after a single clock edge is 0, 1, 0. All right, let me update the outputs. And we see this is now 1. The inputs differ, so the exclusive OR gate produces a 1. And after we apply another clock edge, we see the 1 would get transferred in, 0 transfers in, and a 1 transfers in. So after the second clock edge, these values become evident at the output of the flip-flops. And in this case, since the inputs still differ, we still have a 1 being presented to the lead flip-flop on the left. All right, the new state then is 1, 0, 1. Now we could proceed like this indefinitely, but eventually you start to realize that whatever is in Q0 goes into Q1, and whatever is in Q1 goes into Q2. That's the nature of the shift register. The value of Q0 is calculated as the exclusive OR of whatever is in Q1 and Q2 right now, and that gets transferred into Q0. So let's use this information to see if we can more quickly get at the next state. For clock edge 3, we would say that the 1 here transfers into Q1, and this 0 transfers into Q2. We then evaluate whether or not those are different, and that tells us the value of Q0. And again, they are different, so we're going to get a 1 here. Transfer, transfer. Now they are the same, so we fill in a 0 on this side. And looking at the states, I don't see how any of these looks like the original. So let's keep going. I'll put down 6, 7, and 8. So 0 shifts, 1 shifts. They are the same. Put a 0 here. Shift, shift. They are different. Place a 1 right there. And this looks promising. 1, 0, 0 matches the initial state just fine. So we conclude from this that we needed 7 clock edges to be applied to get us back to that initial state. If we did this one more time, it's interesting to note here that 0, 1, 0 matches where we would get next. So really the sequence that we have tabulated there is a periodic sequence. It will just keep repeating through those values as long as you apply clock edges. Let's review how we approach this particular problem. We set the flip-flop stored values to match the given initial state. We then recognize that the flip-flops are connected as a right shifting shift register. We set the next state of flip-flop 0 to 1 whenever the stored values in flip-flops 1 and 2 differ. We tabulated the progression of states, and then counted the number of clock cycles required to return the flip-flops to the initial state. That wraps it up for this problem.